Welcome back. Today we'll be learning about probability. This is the last chapter in the section of algebra. So what exactly is probability? To understand probability, we first need to know a few concepts. First is a random experiment. So what is actually a random experiment? Well, a random experiment is an experiment all of whose possible outcomes are known to us, but the result of any of these outcomes cannot be predicted. Okay. Now the most famous examples cited to teach the concepts of probability are those of rolling a dice or tossing a coin. Okay. So let us understand it in terms of these two examples. So random experiment, all possible outcomes are known, but we cannot predict the result. So let's say I toss a coin. Now I know the possible outcomes are either heads or tails, right? So I know when I toss the coin. Suppose I toss a coin, I'll get either heads, I'll denote heads by H, or tails, that is denoted by T. So I'm sure that I'll get only these two outcomes, right? These are my possible outcomes. But whether I get a heads or a tail, I just cannot tell that, right? So this is an example of a random experiment. So is rolling a dice or a die, right? So a die, for those who are unfamiliar, it's a cube with the numbers 1, 2, 3, 4, 5 and 6 written on all its faces, okay? On one of its faces. So I know that when I roll a die, the number appearing is said to be the one which is on the top face of the die. Okay, so I get one of these numbers, right? So I know that I'm sure that I'll be getting one of these 6 numbers, but which number I'll get, I absolutely have no idea, right? This is why these experiments are called random experiments. Now probability is all about random experiments. Okay, or we consider our life situations as random experiments and then we proceed. So now that we are clear about random experiment, let's understand what a sample space is. Sample space is a set of all possible outcomes. Okay, so in the case of tossing a coin, the sample space would be H and D, right? That is denoted by S. So S is nothing but H or T, right? This is how you write the set of all possible outcomes. This is one outcome, this is the second outcome. Similarly, in the case of rolling a dice, so these were the 6 possible outcomes, right? So we denote the sample space writing it this. Okay. So this is what a sample space is for. Now an event. The next concept is an event. So an event is any subset of the sample space. Okay. So since this is a set, any subset of this is what an event is called. Okay. So an event is not just, say in the case of tossing a coin, we will not have many events, right? We will have only heads or only tails. Having either heads or tails will actually make the whole set, right? So that is not that interesting. But say in the case of rolling a dice, my event is the number of times I get 1. Okay, so that can be my event. I will not get 1 every single time, right? But I am sure I'll be getting 1 sometimes. Similarly, getting prime numbers. So there are 3 prime numbers here, 2, 3 and 5. So that can be again an event, right? So an event is any subset of the sample space. It need not be only one outcome. Yeah, an event itself can have a number of outcomes, right? So if I say I roll a dice and my event is getting the odd numbers. So getting the odd numbers is 1 or 3 or 5. So my event is getting 1 or 3 or 5. It's not. So you see that there are 3 possible outcomes which come under this specific event. Okay? So this is what an event is. Now, once we know what an event is, there are some things known as equally likely event. Now, an equally likely event. Now, if our dice is not loaded, by loaded I mean that it will not try to give a specific side. A specific side means a specific number, right? Because there is a number associated with every side. So if my dice is not loaded, then I should get all the spaces the same probability, right? Okay. So probability here is just I'll just use it this way. Actually, it's the correct meaning, but so let's understand it this way. So if I toss a coin, I'm sure that I should get either heads or tails. And since say the coin is fair, then both of them are equally likely, right? Because I can get either heads or tails with the same chance of them occurring. So this is what is known as an equally likely event. So say a lady is pregnant with a child. Now if the child can either be a boy or a girl, right? Just not say if it will be a boy, if there is a high chance of the child being a boy or a girl. Then you just can't say it without any other additional information. Right? So this is what is known as equally likely event. Okay, so occurrence has same chances. Right? So all the events have same chance. Now apart from this, we also have mutually exclusive events. Okay. Mutually exclusive event is, it has to be at least 2 now. So mutually exclusive events. So 2 events A and B are mutually exclusive if one of them means the other cannot be, the other event cannot occur. Okay. So A and B are said to be mutually exclusive if the occurrence of one means the other just cannot occur. Okay. So, if A is occurring, it directly implies that B is not occurring. Right? So, suppose I toss a coin and A is the event of getting a head and B is the event of getting a tail. Now, if I get a head, which implies that my event A has occurred, that directly implies that my event B, which was having a tail, does not occur, right? So these 2 are mutually exclusive events. Similarly, suppose my event is getting a if I roll a die and if my event A is getting odd numbers, my event B is getting an even number. Right? So once I get an odd number, it is already I already know that I just cannot get the even number, right? So one event occurring directly implies that the other event is not occurring. These kind of events are called mutually exclusive events. Finally, we have something known as exhaustive events. So, exhaustive events are the set of all events such that the total number of possible outcomes are all of them are covered under those events. Okay. So, let's say I roll a die. So, I am supposed to get the numbers from 1 to 6, right? Now, suppose my event A is getting an odd number. P is getting a prime number, right? Now, if A is getting an odd number, then all my favorable outcomes for A, these will be 1, 3 or 5, right? Similarly, for B getting a prime number, the favorable outcomes are 2, 3 and 5, right? So suppose I just consider these two events, A and B. Now, if I roll my die, and suppose I get say 4. Now 4 is not under either of these events, right? So I can see that these events are not exhaustive. Okay? So A and B are now not exhaustive, because if they are exhaustive, then every possible outcome of that experiment should be covered under one of these events, at least one of these events. Now suppose I say C is getting the composite number, right? So the composite numbers here are just 4 and 6. Okay, so you see that actually now all of the outcomes are covered under at least one of these events. So now I can tell that A, B and C are exhaustive events, right? Similarly, I can say that B and C, now we just consider B and C, you have 2, 3, 5, 4 and 6. So 1 is missing, right? So B and C are not exhaustive events. Similarly, even A or C are not exhaustive events, right? And you can make such combinations again. A and B similarly are not exhaustive events. Only A, B and C here are exhaustive, and when all of them are considered together, then they are exhaustive events. Okay. Let us now move to the concept of probability. So probability is the ratio of the number of favorable outcomes of a particular event to the total number of outcomes for the experiment. Okay. So it is usually denoted with a small p, is lowercase p, and the definition, or I'll write it the formula. So it is the number of favorable outcomes, the total number of outcomes. Okay. Now, if P is the probability of that event, because P is called probability of event A. So this is written as just P, or you can write it more descriptively as P of A, right? So this is P of A. So this is equal to number of favorable outcomes for the event A divided by the total number of outcomes for the experiment. Okay. Now, if P is denoted by this, obviously the non-favorable outcomes and the ratio of that to the total number of outcomes is denoted by P bar. Okay. And this is written as 1 minus P. Or you have P plus P bar is equal to 1. Okay. So if P is the occurrence of event A, P bar is the non-occurrence of event A. Okay. So, and we have a very simple formula: P plus P bar has to be equal to 1. Also note that P, since the total number of favorable outcomes of any event cannot be more than the total number of outcomes, and moreover, since we are talking all about real cases, this is probably the most important and also the most trivial result we get for P. P must lie within the interval 0 to 1, but it can take any number of values inside, any number of real values, there is just no kind of restriction on that. But it must be between 0 and 1. 0 and 1 obviously inclusive. 0 means the event is an impossible event. The event will never occur, right? So if I roll a dice and my event is getting the number 8, I'm sure that will never occur. So that comes under an impossible event, and the probability is always 0. Moving on. So I just write the few notations which we'll be using here. Suppose we have an event A. Okay, so that means the event A is occurring. Okay, we will always be worried about this part. Suppose I consider event A and say P of A, that means event A is occurring. Now, if event A is not occurring, just like I wrote in the previous slide, instead of like P bar, I can write A bar or A dash or A and then the superscript C. That actually stands for complement. This means event A is not occurring. All of them have the same meaning. One can write any one of these three expressions. The next we have is A union B. So this symbol stands for union. And this means either of the events is occurring. We can have both the events occurring too. So this is known as A union B. Similarly, we have A intersection B. So that symbol actually stands for intersection, and that means both the events are occurring. Similarly, the notation this is used more in set theory. So this means this is a subset of A is a subset of B. That means if A occurs, occurrence of B is implied. Right? So these are the most important notations we will be using here. A union B, that means either of the events A or B, A and B is occurring. A intersection B means both of them are definitely occurring, and A subset B means if A is occurring, B has to occur. Now, a very important tool in analyzing various situations or even solving them is this thing known as Venn diagram. Okay, so we'll be seeing more practical usage of this concept. I just mention it here. So suppose I denote my sample space by this rectangle. You need not make it a rectangle, you can make a square or whatever. This is just the usual way of doing it. Okay, so suppose this denotes the occurrence of event A, and this denotes the occurrence of event B. Okay, so now all of this is event A, right? And similarly, all of this is event B. But if you remember, there was this small part which gets or which is actually shared by both of them. So this is the part known as A intersection B, right? Because here the event A is occurring and at the same time event B is also occurring. Whereas this whole part, this whole shaded part, right, all of this is known as, or that can be written as A union B, right? Now at the same time, if you just consider this part, so the only A in the circle, everything else is nothing but A complementary or A dash or even A bar, right, which is equal to 1 minus A. Or in this case actually we should write not 1, we should write U or the universal set or even the sample set S, right? So this everything apart from A is nothing but the complementary event of A. Okay. Similarly, for B also we can find out. So if this is my event B, everything else will come under B star, B dash. Okay. Similarly, I can consider A union B as an event, and I can find out A union B whole bar, right? Suppose this is my A union B, everything else here, right? So everything else in this space will come under as A union B whole bar. I can even consider A intersection B, and again I can consider the complement of that. So the point here is you can consider anything as an event and correctly apply all the related concepts of complement, and they are found to be correct. Now here is a very basic and important result. I write the general result. So this is P of E1, E2, E3 all the way to En. So equal to P equal to 1 to N of P of Ei. Right. This is my formula. Now let me explain everything here. Suppose I have n events by the name E1, E2, E3 till En, all obviously under the same experiment. So the left hand side here means the left hand side is the union of all these events, right? So the P of that means the probability of any of these events occurring, right? So the left hand side is probability of any of the n events from E1, E2 till En occurring, and that must be equal to, the first term is sigma P of Ei. So I'm considering all the events individually now. So the first term expanded will be P of E1 plus P of E2 plus P of E3, right? Now that's subtracted by P of E1 intersection Ei intersection Ej. Now I'm considering all the events piecewise. I'm considering all of them individually, and then I'm just taking the intersections. Okay, so I'm considering all possible selections of two events at a time, and I'll subtract that part. Then I'll add all the possible selections of three events at a time. Okay, and similarly the process will go on till the last one when I consider all of the events occurring simultaneously. Okay, so this is a very important formula. Definitely it has been generalized, and we'll be using more of this formula in its simpler forms. So which will include two and a maximum of three terms, three events. So if I write it for two events A and B, So I have only E1 and E2. E1 is A and E2 is B. What I get is P of A union B is P of A plus P of P minus P of A intersection B. Okay. So this is a very simple result here. P of A union B is actually related to both P of A and P of B minus P of A intersection B. That should have been pretty clear, right? If this is P of A, this is P of B, P of A intersection union is B. Now we saw that this part was actually getting the part shared both of them. A intersection B was actually being shaded twice. So we needed to remove it once or minus P of A intersection B. Right? Now we had some time back learned about mutually exclusive events, right? So if E1, E2, E3 and so on till En are mutually exclusive events, then obviously they do not share anything common between them, right? So all of their intersections will yield nothing but 0, right? So this part is important. Understand that mutually exclusive means that P of you consider any two events or even more, and if you try to find out their intersection part, that has to be 0 because they are mutually exclusive to each other, right? So if I consider n events, the same n events, let's say, and I put the restriction that they are mutually exclusive, then the same result actually reduces to just the first term, sigma P of EI, right? Because the second term is 0, the third term is 0, and so on. All of these terms have to be 0. Okay. Now let us look at another concept known as conditional probability. So conditional probability is actually written this way: P of A divided by B. You can make it a proper horizontal line also, or a slash also will do. So P of A divided by B. So this is pronounced as P of A given B, and it means P of A given B. It's always written in the formal way, only in this way, not this way. So this means the probability of the event A occurring given at B has already occurred. Okay. So this translates to probability of event A occurring given that B has occurred. Right? So this is the definition of conditional probability. Now we have a very simple formula for P A given B. And this is nothing but P of A intersection B by P of B. Okay. So actually just transforming this, we actually get an equation for P of A intersection B. This can be written as P of B into P of A intersection B, A given B. And this can also be now just changing the places of A and B. We get the second formula. So there are actually two different ways of expressing P of A intersection B. Obviously, since both of them can be interchanged, right? We are writing a general formula. So we get this. Okay. Let us now look at independent events. So independent events, as the name doesn't suggest, are those events which do not affect each other's chances. Okay. So if I have two events A and B, if A occurs, the occurrence of B, if that is not changed, that is not affected in any way, then I say that A and B are independent events. Actually, this works both ways. I mean, I should have both of them not affecting the other one, right? So, even if A is not affecting B, but if B affects A, then I cannot say that A and B are independent events. So, independent events are those events should not affect the other events' chances. Right? So, say I am rolling a dice and my events are, say, one event is having an odd number, the second is having an even number. Actually, these are actually also mutually exclusive events, and I also see that these are also independent events, right? So, if I have whether an odd number has come or not, that actually doesn't affect the other number. When it does, that both of them actually become zero. But then that is what an independent event is, right? So these events do not affect the other events' chances. Okay, so now independent events will be the same. If this is the case, then we can write some very simple equations for these. First of all, P of A given B. Now suppose A and B are independent events, then P of A given B, whether P has occurred or not, should not anyway affect the chances of A, right? So this must be equal to P of A. Similarly, P of B given A, if again A and B are independent, must be equal to P of B only, right? So in other words, I get that if A and B are independent events, I can write P of A intersection B as P of A into P of B. So this is a very important result. If I have this case, then I can, after some investigation, also say that yes, the events are independent. So it works both ways. Similarly, if there are n independent events, E1, E2, E3, E4 till En, right? If all of them are independent events, then I can write, just extending the above formula, this thing will be nothing but the individual probabilities multiplied to each other. Right? So that is this is for independent events. Next we have there are a few offshoots from this. There's something called pairwise independent. These things obviously are important only when we consider 3 or more events. For less than 3, that is for 2 events, this doesn't make much sense. So pairwise events are, suppose we have 3 events, E1, E2 and E3. Now P of E1, E2 intersection P of E1 and E2, that must be equal to P of E1 into P of E2. Similarly, I can write for E2 and E3 and also for E1, E3. Right, but I cannot say anything about P of E1 intersection E2 intersection E3. So this is what pairwise independent means. So if I consider the events pairwise, right? So I may consider them E1 and E2 or E2 and E3 or E1 and E3. Then I get the last result is actually wrong. There is no there is no E2 here. We have E3. Right? So if I consider any two events pairwise, they are independent. So just extending this the next one is known as mutually independent. Now, mutually independent events are obviously pairwise, and they have another extra component. Suppose E1, E2 and E3 are mutually independent events, then they are pairwise, plus they also satisfy the next result, that P of E1, E2 and E3 intersection is actually equal to P of E1 into P of E2 into P of. Let us now look at the total probability theorem. Okay. Now, let us say our experiment has our experiment can be divided into n different mutually exclusive and mutually exhaustive sets, right? So I have n mutually exclusive and exhaustive sets, right? Now, since they are mutually exclusive, I can guarantee that when one of them is occurring, the other one is not occurring, right? And exhaustive means all of them combinedly will give me the whole set, and hence all of my possible outcomes are actually covered under all of these events, right? Under at least one of the events. Now, if I consider any event E, which may be a subset of any of these events, or it could be, say, a summation of 2 or 3 events, right? It could be union of a few events, or it could be any mixed thing. So, if I just consider event E, I can always write P of E in this format, right? So, it has a very simple meaning. Try to understand it this way. So the term means P of AI into P of E given AI, right? So since I have n different mutually exclusive events, let's forget exhaustive for now. So this event actually means, first let the event AI occur, and once AI has occurred, now given that AI has occurred, what is the chance of the event E occurring, right? So I consider it for that part. Similarly, now I move to the next one, next event, say A2, and similarly look at the probability of the event A2 occurring, and then chances of event E occurring, given that A2 has already occurred, right? So I then add these things up, right? Because these are mutually exclusive. So event A1 occurring, and then the subsequent event E occurring will have no collapse. Sorry, they will not collide with each other, right? So obviously, I will not be counting any extra part. Similarly, I will not be missing out anything else, right? And now, since these are exhaustive, hence I am covering the whole of the event E, right? So I can write P of E is the summation of these terms when they are summed over all I. So this now gives rise to probably the most important theorem in probability, known as Bayes' theorem. Let us first write what Bayes' theorem states. Right. Now here AI actually is any of the n mutually exclusive and exhaustive events A1, A2 till AN, and B is any other event. Right? So B can be any of these AIs, which will be a very trivial case, or any other event of the experiment, right, which has no connection with these AIs. Right? So what the experiment actually, what the formula actually says is, now suppose we know that our event B has occurred, so what is the probability that a specific or a specific AI event to have occurred, right? So the probability of the event AI given that B has occurred, so that is actually given by P of AI into P of B given AI divided by, if you look at the denominator, well, it's nothing but P of B, right? From the previous formula we know that this is nothing but P of E, so here it will be P of B, right? So that actually is summed over all i's, and hence you get total probability of the event B. So this is actually a different way of writing the equation we wrote for conditional probability. We're just moving the terms here and there a little, and you get this theorem. A very simple proof exists for this, and any standard book can actually give the proof. So I'm not going to that. But remember this formula, and we will be seeing a lot of its practical usages in the questions in the next video. Finally, there is something known as binomial distribution. Again, a distribution very common in nature, and it's also something which we deal with in day-to-day life. Okay. Now suppose I have an experiment which has only two possible cases, right? So either I have case A or case B, and suppose case A is okay. Let us say take the case of an examination, right? So if you write an examination, you have two possible cases, whether you pass or you fail, right? So this kind of distribution is known as a binomial distribution, which has only two possible outcomes, right? Suppose you toss a coin, you get either heads or tails. Again, binomial, right? So suppose the probability of one of the outcomes. Okay, let us now consider only one of the outcomes for us. So suppose I take the probability of that event occurring as P. Okay. So P is, for me, that is success, right? And I'll call Q as the failure. Obviously, because Q is mutually exclusive event, right? And at the same time, Q is 1 minus P, or Q denotes that the event important to me not occur, right? Now suppose I conduct this experiment n number of times, and I want to see if I am having r number of successes. Then this is given by a very simple formula. Okay, I just change this P, and this will confuse with the normal P. So I'll write this as capital P of R. Right. So what this means is I repeat my experiment n times. So n times experiment has been performed. And I want to see what is the probability of R successes. Right. So suppose I toss my coin, say 100 number times, and I want to know what is the probability of say 40 heads, right? So I don't know. With additional information, I know whether what the probabilities of a single head or single tail have or are, and So using this formula, I can find out the total number, the probability when repeating the experiment n times, and I want to see the r number of successes. Okay, so this is the formula, and actually if you look at this and if you try to sum it over all the possible number of successes, that would include, say, r is going from 0 to the maximum number n. Well, what do you get? If you try to look at the right side and if you try summing it out, you should get what we did in the previous chapter, right? So this is nothing but p plus q power n, right? And we know that p plus q is nothing but 1. So this is 1. That is what we are supposed to get, right? So suppose I repeat my experiment n number of times, the probability of all the possible cases, right? So suppose I'm doing my tossing a coin 100 times, and right from the probability of 0 heads to 1 head, 2 heads, and similarly 3 heads, 4 heads, 10 heads, 15 heads, 20 heads, like this, till 95 heads, 96 heads, 98 heads, 99 heads, 100 heads. If I sum all these probabilities, then I should get 1, right? Because that is the total number of cases of the experiment divided by the total number of cases of the experiment should give you 1. So this is actually just a verification of our formula, and you can see that this is actually correct. So that is it for the theory and formula of probability. Stay tuned for the questions which we will be taking in the next video.